All right, so welcome to the recitation session for the first test.
In Florida, there's a special lab studying lightning. ABC's Bill Blakemore went to pay a...
All right, so a number of questions that we should be able to answer, right? So we need to be able to answer the question of what lightning is and how the lightning comes about, where the lightning comes from. And on top of that, we won't be able to answer this fully in this chapter, but as long as you're inside a metallic enclosure, somehow you're going to be safe. All right, so we're going to be able to answer high ground versus the low ground, which one is more likely to be struck by lightning? The answer to that question is high ground. So the question is why, if that's the case, that high ground is not the one that gets struck by lightning 100% of the time. All right, so we won't be able to answer that question this week. It's going to be next week. The sort of stuff that you have to worry about is charge cone attracting water, despite the fact that the water is neutral. Plastic wraps clinging to glass as well as porcelain, despite the fact that the glass and porcelain are neutral. So how's that happen? How did that happen? All right, so we know that the charged objects will either attract or repel. So the attraction and the repulsion can be explained, assuming that there are two kinds of charges. Right? So the like charges will repel, the non-like charges will attract. All right, so these charges are particles. You will find them in atoms in nature. Atoms will contain equal number of positive and negative charges. Positive charge is going to be at the center of an atom. The negative charge or charges will move about the center of the atom. All right, so the positive charges will be at the center, and negative charges are going to be moving about the center of the atom. Okay, so these are known as the unit charges. They could be positive or they could be negative. Positive photon, the negative electron. And both of them will have the same value. All right, so one of them is going to be negative, the other one is going to be positive. The unit is going to be coulombs. All right, so you can have charges in bunches. All right, so sum total of all charges is known as the net charge. All right, so the formula that we will get to use for that is going to be this. So Q is the net charge and is the total number of charges that you have. And then the lowercase e is going to be our unit charge, positive or negative. So the net charge is the sum total of all the charges that we got. So in this case, it's going to be -4. All right, so when you put positive charges in it, now it's going to be -3, -2, -1, 0, and then it's going to be positive. All right, so if something is negative charge, it's got more negative charges than positive charges. If something is positive charge, it's got more positive charges than negative charges. If something is neutral, it's going to have equal number of positive and negative charges. Charges cannot be created or destroyed. This is known as the conservation of charge. Smallest negative unit charge that you can think of is an electron. So you cannot take an electron and break it into something smaller than itself. All right, if the charges cannot be created or destroyed, how do we charge something up positively or negatively? All right, so the process of charging something up positively or negatively is known as ionization. All right, so it's the term implies that you're stripping electrons from atoms. You do it through friction, you do it through heat, or you can do it through light. All right, so the example that we're focusing on in this chapter is the lightning phenomenon. All right, so the clouds become ionized initially because of friction among ice particles. And for some unknown reason, the positive charges go up to the top of the clouds, the negative charges sink to the bottom. So which means that the clouds become polarized. And once the clouds become polarized, the ground, which is initially negative charge, will become positive charge through a process called polarization, something that we will discuss shortly. All right, so the initial ionization of the charges inside clouds will take place because of friction among ice particles. Once you strip the electrons, you can transfer these electrons from one place to another. The materials capable of doing that are known as conductors. So the metals are good conductors. Living things are good. Insulators, on the other hand, not so much. All right, so they're not good at conducting. So the reason why the conductors conduct, because the octet rule is not satisfied. Octet rule is the tendency of an atom to complete its atomal shell up to 8 electrons. So that rule is not satisfied. So as a result, what they do is, in order to satisfy the octet rule, they do electron share. So they get to share the atomal shell electrons. These are known as the conduction electrons, or the valence shell electrons. Insulators, on the other hand, are not good at conducting these free charges because the octet rule is satisfied. So the free charges are not able to attach themselves to any of the atoms or the molecules, in essence. All right, so that's an explanation from classical physics. In this scenario, the foam is negative charge. Water is not positive charge, it's neutral. So how is it that the negatively charged comb able to attract water? Well, the reason why that happens is because of something called polarization. All right, so comb is negatively charged, paper is neutral. What's happening is the atoms within atoms or within molecules, the charges rearrange themselves in such a way that the opposite charges become closer to the negatively charged comb in this case. So the surface becomes positively charged as a result. And the like charges will be repelled from the surface. The unlike charges are pulled to the surface. As a result, the surface becomes polarized. So the opposite is charged. That's the meaning of it. All right, so the comb is able to attract paper because within paper, the charges rearrange themselves. So the opposite charges are pulled and the like charges are repelled into the surface. So the surface becomes polarized, which means that the surface becomes oppositely charged, despite the fact that the material itself is still neutral. So the same thing is happening here. You've got a plastic wrap, which is uniformly negatively charged. And then you're able to stick it to glass because the glass, which is neutral, becomes polarized. It's still neutral, but the surface becomes polarized. So the surface becomes oppositely charged. The opposite is charged. So the electroscope, once again, is the setup. So there will be a bunch of questions on the time. This is otherwise known as the gold leaf electroscope. So this tends to be, these are the gold leaves usually. They don't need to be gold, but for whatever reason, that's what's being used. All right, so the contraption inside is a metal piece, so it's neutral. So if you bring a negatively or positively charged rod nearby, it becomes polarized. So the top, in this case, positively charged, the bottom is negatively charged. Notice that the like charges will repel. If you touch this negatively charged rod to the metal piece, the charges get transferred to the metal. As a result, the metal piece is going to have a negative excess charge. Excess charge meaning that's going to require a negative charge, net charge. So this is known as charging by contact. Also, you can charge by induction. All right, so charging by induction means that, number one, you will polarize the metal piece. Notice that there's a metal piece or sphere, which is insulated from the ground. You have a rod, positive and negatively charged. Immediately, this charged rod is going to polarize the sphere, metallic sphere. So if you ground this metallic sphere by using a grounding wire, right, so it's going to force the like charges. In this case, like charges are the negative charges. This rod is negatively charged. So the negative charges inside the sphere is going to be forced into the ground. If you get rid of the grounding wire, it's going to have a net positive charge. So the net positive charge is going to remain where it is. Obviously, it gets pulled to the surface because of the electrostatic attraction. And the like charges will be forced into the ground. And if you get rid of the grounding wire, it's going to have a positive net charge. So this is known as charging by induction. All right, so the electrostatic force is the force between charges. All right, so from this setup, it's fairly obvious that the charges are separated inside the piece of paper. Piece of paper becomes polarized, so this end has a positive net charge, opposite end has a negative net charge. This paper is going to be attracted to the negatively charged comb because of the simple reason that the positive net charge is a smaller proximity to the negatively charged comb than the negative net charge inside the paper. All right, so which means that the distance is going to matter. Distance is going to matter in terms of this force. All right, so when the charges are closer by, force is going to be larger. When the charges are further apart, the force is going to be weaker in essence. All right, so the person who noticed this is Coulomb, and he was able to come up with a formulation for it. And the formula looks like this. All right, so the force is going to be directly proportional to the product of the net charges. It's going to diminish with distance is the square of the distance between these two net charges. So these are two separate net charges. And K is going to be the strength of this electrostatic force, known as the electrostatic force constant. So K is a big number in this case. It's going to be almost 9 billion that you're looking at. Force structurally electrostatic force looks like the gravitational force because the idea is plagiarized. Idea as well as the format is plagiarized from Newton, meaning that he copied the idea without giving credit to Newton himself. Though the force itself is distinctly different. The electrostatic force is different from the gravitational force. It's much, much stronger, right? Gravity is only attractive. Electrostatic force can be attractive as well as repulsive. And those are the major differences. All right, so one of the things that you will have to notice whenever you're applying this force in problem solving is this formula is meant to give you a number only. All right. It's meant to give you the magnitude of the force as it is. Our force is a vector, it's got direction. This formula is you're using it as is, it only gives you the magnitude, it gives you the size of the force. because it's giving you the size of the force. Positive or negative doesn't matter. All right. If you come up with a negative number, negative does not mean anything. It's like negative time. All right. It doesn't mean anything. All right. So which means that if you have any negatives, you have to just get rid of them for further calculations, because the positives and negatives are direction indicators, which means that they're related to vectors. So if you're doing a scalar calculation, if you come up with a negative when you're using a force formula, make sure that you get rid of the negative. So how do you get rid of the negative? And you get rid of the negative because the negatives usually come from these charges, which means that you have to take the absolute values of these charges in your computation. All right, so this is the Bohr's atomic model. I'm not going to go over the problem. Okay, so this is for those of you guys who are taking university physics, fact-based physics. All right, so the extra credit portion of the math, and there's going to be an extra credit, which is going to be done in person, which is going to be done in class during the lab hour. All right, so this is one of those problems I want you to be able to do in your sleep. Okay, so the Bohr's model of the atom, the hydrogen atom, is a big thing in physics because we will be following it through the history of physics. We will be following its evolution through the history of physics. I want you to be able to do this stuff in your sleep. I want you to know this stuff so well that you need to be able to do this stuff inside out. So which means that you have to go back and watch the lecture video, and you need to practice this and practice this and practice this until it's second nature. All right, because we will be going through the history of this until the end of the semester. This is the simplest model of the atom. And the entire classical physics, electricity and magnetism, is based upon the Bohr's atom, in essence. All right, so every time we learn something new, we're going to apply it to this model so you can see what's going on inside the atom. All right, so which means that when you guys are studying, not necessarily for the weekend test, but when you're studying for the extra credit, make sure that this is already ready and available in your heads. All right, so the only thing you will get to use is the formula sheet. You're not going to be able to have any access. You're not going to be able to access this material during the test. All right, so the next question is, how do these charges communicate with each other? How does the force get communicated? So the force usually gets transferred or communicated through the electrostatic force field, which is known as the electric field. Positive charges are the transmitters, negative charges are the receivers. So it's a visual model that we came up with. When I say we, I mean only one person. His name is Faraday. So Faraday is the guy who came up with it. And the reason why he came up with these visual models is because the guy can do math. That's it. All right. He's the last of the physicists in the history of physics who could not do math. All right. And before you guys feel really confident that you're somehow better than he is, I got news for you guys. Faraday ranks up there with Newton. He ranks up there with Einstein. All right. Without Faraday, we wouldn't have this technology that we have, electronics-based technology that we have. This communication that we're having right now would not be possible. All right. So this guy who gave us almost half of physics could not do math, but he literally, this guy is the reason why we enjoy electricity and magnetism-based technologies, as well as anything and everything related to electromagnetic waves. All right, just imagine that. And the guy just couldn't do math. All right, so which means that the physics can be done conceptually. And that's exactly how this guy did it. All right, it's conceptual, it's visual. Positive charge is the emitter, the negative charge is the receiver, and then that's the model that he came up with. All right, so the positive charges will transmit the field, the negative charges will receive the field, the like charges will repel, the unlike charges will attract each other. All right, so the electric field lines will start on positive charges, they will end on negative charges. Electric field emitted by this positive charge is going to act on this positive charge. So the electric field interacting with this positive charge is going to induce a force on it. So the electric field acting on this charge is going to induce a force on it. The electric field from the first charge acting on the second charge is going to induce a force on it. All right, so these are the models that he came up with. Okay, so that's the mathematical illustration of the model. Electric field acting on the charge is going to induce a force on it. All right, so we got two opposite charge regions. There's going to be a constant electric field in between. And when you place the positive charge within that region, all right, so the force acting on the positive charge, electric field acting on the positive charge is going to induce a force on it. As a result, this positive charge is going to accelerate in the direction of the force. Electric field acting on the negative charge will experience a force on it in the opposite direction of the electric field. Positive charge is going to accelerate in the direction of the electric field. The negative charge is going to accelerate in the opposite direction of the electric field. And if you place a neutral atom within this region, it's going to become polarized. All right, so the negative charge is going to get pulled in the opposite direction of the electric field. The positive charge is going to get pushed in the direction of the electric field. As a result, this becomes polarized. So now that the negative charge is closer to the source of the field, which is the positive region, it's going to experience a net force in that direction. So the entire atom is going to accelerate in the direction of the positive charge region. All right, so lightning phenomena. Lightning is, you can say that it's born in the clouds, or you can argue that it's born on the ground. So either way, either explanation works fine. All right, but for the lightning to happen, the first thing that needs to happen is obviously there's a charge separation inside the clouds. Top positive charge, bottom is negative charge. Negative charges will pull the positive charges to the surface, and so we end up getting to opposite charge regions. So the negative charges start to come in the downward direction. They are being pulled in the downward direction by the positive charges on the ground. And the positive charges from the ground are pulled in the upward direction by the negative charges under the cloud. All right, so the train of these negative charges is known as step leaders. So they're coming down in high concentration. And the train of these positive charges going up from the ground, these are known as the streamers. So when they make contact, there's going to be an electrical discharge. The electrical discharge is the opposite of ionization. All right, so the discharge is, hey, this atom needs an electron, it's got a missing electron, so guess what? It just captures an electron. This is an electrical discharge. All right, so it's the opposite of an ionization process. Electron is moving fairly fast, it's got kinetic energy. Atom is moving relatively fast, it's got kinetic energy. So what happens to the kinetic energy upon the electron being captured? So it turns into heat, it turns into light, it turns into sound. All right, so that's the short explanation. More in-depth explanation is what's happening is this electron being captured, it's got tremendous amount of energy, so it needs to lose its energy. So what it does, it tries to free itself by jumping around inside the atom. Call it quantum jump. Every time the electron jumps around, every time it undergoes a quantum jump, it's going to lose its energy in the form of light. So that's where the light. When the electron is going nuts inside the atom in response to that, it starts to vibrate. All right. So that vibration motion is known as heat. So the heat comes from the vibration of the atom. All right. And then what happens? The sound is generated. The sound is usually generated because the area within this region heats up quite a bit because of this heat. So there's a sudden expansion of the air, creates a partial vacuum, and then air collapses into that vacuum. So there's a lot of collisions that take place among the molecules. So that's the reason why you end up getting the founding. All right, so the stuff that doesn't make sense in this model is these positive charges coming up from the ground. These positive charges coming up from the ground are not the same as these charges. All right, so the ground becomes polarized. In essence, the ground is still more or less negatively charged, but the negative charges are repelled into the surface, pushed into the surface, and positive charges are pulled to the surface. These are, which means that the surface is just polarized. All right, these are not free charges. They're not free to move up from the ground. These are positive ions coming from somewhere, and we don't know where these positive ions are coming from. In essence, they just get pulled out of the ground, and they start to move in high concentrations in the upward direction. So when the step leaders meet up with these the streamers, and then that's when the lightning is. So that's the second mystery of lightning. The first mystery is the polarization of the clouds. The second mystery is the positive charges coming from the ground, positive ions coming from the ground. All right, so problem number 5 from the handout. This is the one you need to practice. Okay, so I'm not going to go over it because just go back to the lecture video I'm watching. Okay, so those of you guys who are taking university physics, this is the one that I want you to practice. Okay, so I'm going to give you a region, just like in this one. I can give you a region where the electric field is going to be pointing in one direction. In this case, the electric field is pointing along the next direction. And then we can introduce a charge into this region, and the charge is moving on the vertical direction. And then I can ask you the speed of the charge, like 3 seconds later, 5 seconds later, or whatnot. Okay, so this requires you to be able to draw things out, identify each and every single vector, and then just do the analysis of it. So what's happening is the electric field is going to induce a force on the charge on the x direction. And so this charge is going to accelerate in this direction while maintaining a vertical speed. So 3 seconds later, it's going to have a speed on the vertical direction, and it's going to have a speed on the horizontal direction. And if you know the components of the speeds on the x and y directions, you can figure out this final speed, the resultant speed at that point. And then you can also figure out the direction of that motion. All right, so this would be this sort of question that you can see on the test if you're taking calculus stations. Okay. And for you to be able to solve this problem, obviously, you can use the kinematics equation. All right, so electric field due to a point charge. I'm gonna just skip through the basics. All right, you get to use this formula only if it's a point charge. You get to use this formula only if it's a point charge. That's it. So it could be a point charge could be a net charge. It doesn't need to be a single charge. It's a net charge. It could be a region of some kind of a net charge. And it's gonna look like a point charge from a distance, in essence. All right, so this is a positive net charge, it's a positive point charge. This formula says the strength of the electric field transmitted by this point charge depends on the charge itself. If the larger the net charge is, the stronger the electric field is going to be. And also it depends on the radial distance relative to that point charge. All right, so further away you are relative to the point charge, the weaker the field is going to be. So the strength of the field is going to diminish inversely as the square of the distance. Once again, guys, this formula is for a point charge. Okay, so you will have like 3, 4, 5, 6 different electric field formulas. And then every time you look at a formula, make sure that you understand what that formula represents. So these formulas are geometry sensitive. All right, so if it's a point charge, it's going to be different. If it's a surface charge, it's going to be different. If it's a conductor, it's going to be different. If it's an insulator, it's going to be different. Shape is going to matter. The geometry is going to matter. The relative distance is going to matter. So every time we do a derivation, every time there is a formula, just take note that you cannot use these formulas blindly. All right, so these formulas are used depending upon what the geometry is. All right, so this is the strength of the electric field. This is the electric field formula for a point charge. All right, so there will be a bunch of multiple choice questions like that. Okay, so this is for the setup of these problems. Okay, so how do you set it up? I can put 2 net charges next to each other, positive or negative, positive and negative, or negative to negative, it doesn't matter. I can ask you about the total electric field nearby. All right, so these fields are vector fields, which means that they have directions. At this point, P that you're looking at, P stands for point. Electric field due to the positive charge is again pointing to the right. So here's the electric field due to the positive charge. And at this point, once again, the electric field due to the negative charge is again pointing towards the negative charge. So what is the total for net electric field at this point? So what do? You do a vector addition, in essence. So you sum up the electric field contributions at this point. All right, positive charge, the positive electric field is pointing to the right. And the electric field due to the negative charge is pointing to the left. So this direction is positive, opposite direction is negative on the x direction. All right, so these are point charges. So we use the point charge formulas for the electric fields. All right, and then we specify this radial distance between the positive charge and this point and negative charge on that point in these formulas. So make the adjustments to the formulas accordingly. And then we do a back substitution of these formulas. And then depending upon the geometry, obviously you solve the problem. So you guys have seen an example problem regarding that. All right, so this was problem number 4. If you want to see an example problem, take a look at this from the lecture. Okay, I'm not going to go through it. This is straightforward. You may end up having questions like that. You will definitely have questions like this on the multiple choice section of the problem. All right, so those are the things to focus on. Problem number 3 is an example of this sort of problem. I'm not going to do it here. I've done it during the lecture. It can get involved. Your multiple choice question should not be this involved. All right, so your multiple choice.
Sir, quick question to ask. Sir, so the lecture video you have up right now is like 2.5 hours. Is that going over like the same material that you went over last night as well? Because I wasn't in class last night due to
no, it's different. Last night's material is for next week's lecture.
Well, correct. It's for next week's, but I'm talking about like the rest of the electrical field and magnetic that you went over that you finished, I guess, yesterday.
Okay, so the yesterday stuff is not related to this week's test.
Okay.
Okay, so all right.
I'm checking if because I know you said you still had to edit your videos until like Friday, but I was wondering if the video you have posted right now is that fine to study that video?
Okay, so yeah, absolutely. The lecture videos are already done, so they don't need editing. Only video that I'm going to edit is this one.
Okay.
The recitation video is the only one I'm editing. That's it. Yeah, you can use the lecture video just to study for the test, basically.
Yeah, because I was gonna try to make it at 8, sir, but yesterday we were like standby for Star on the boat, and we were just like kind of waiting around. I'm at work right now, but I'm just like sitting here.
Yeah, I figured. I understand your commitment, so I figured. Yeah, that's fine. So lecture video has everything you need in it. That's what I'm outlining here. I see. Focus on this problem, focus on that problem. In essence. Okay, so that's it. All right. So the only video that you have to worry about is what chapter is this? The only thing you have to worry about is the lecture video, yeah. From that chapter, whatever the chapter number was. Was
Yeah,
it 23?
I watched it already, but I didn't know if you went over any other material other than like
No,
like added on. So I'll just rewatch it again.
Okay.
Just to refresh
I
my
mean,
mind.
when you guys are rewatching it, just focus on the sections that I'm outlining, right? In terms of studying for problems. I'm just telling you what's important. Just go back and take a look at those problems. And this problem in the multiple choice section of the test, this is, I wouldn't ask you something like this on the test because I think this is a little bit too simplistic. At the same time, the math gets kind of convoluted, so I don't really care about convoluted math. I just want you guys to get to the point. But just focus on the simple stuff. Like problem number 3 is a little bit too convoluted, but this example, problem number 4 that you guys are looking at, this stuff is straightforward. Be able to set this up and be able to do it. This is the sort of stuff that I'm looking for. All right, so a couple of things here. Derivation of this one is not that important, okay, but the meaning of it is. Okay, so this is the electric dipole. So what does it mean? So the meaning of it is you're looking at a region, literally. From outside, it looks like there's an atom there, the atom is neutral. All right, so from outside, when you look at it, you're not going to be able to pick up any sort of electric field if you're at a large enough distance away from it. All right, and all of a sudden you go, okay, so you see this blob, it's an atom or a molecule, it doesn't matter. All right, it's neutral, meaning that there's no, you're not going to be able to read or pick up any sort of electric field. And then you're thinking, okay, so if that's that region that looks like an atom or a molecule, yeah, you understand that there are charges inside, but it's got equal number of positive and negative charge. So the question is, are these positive and negative charges are next to each other, or are they separated? All right. So if there's any sort of separation distance between these charges, net charges that you're looking at, if there's any sort of separation distance like D that you're looking at, if you come close enough with your probe into this region, all right, if you come close enough to this region, you're going to start to pick up some electric fields. Okay, you're going to end up picking up a very weak electric field. So if you're able to get an electric field reading in a region which is close enough to this atom or a molecule, that implies that there's a charge separation. All right, so that implies that these charges are not sitting next to each other. These charges are sitting at an approximate distance from each other. All right, so the distance, so there's going to be a separation distance between opposite charges within these structures that you're looking at. That's what it means. All right, so electric dipole is a vector. Okay, that comes about when opposite charges are separated from each other. And the electric dipole always points from a negatively charged region towards the positive charge region, or from a negative net charge towards a positive net charge. All right, so that's the meaning of it. So electric dipole means that within that structure of an atom or a molecule or whatever, opposite charges are separated from each other. That's what it means. So the derivation itself is not that important, but the meaning of it is important. So this is the formula that we end up getting. So this region where you're trying to get the electric field strength is going to be due to an electric dipole, which means that there's a net charge and there's separation between the net charges, opposite net charges. All right, so the separation is distance is going to be d. And the strength of the electric field is going to diminish rather quickly. All right, so if you're close enough to this region, you're going to be able to pick up an electric field. Now let's move forward. All right, so if you're close enough to this region, for a single charge, the electric field is going to diminish as the square of the distance. So if you're further away, you're not going to be able to pick up a strong enough electric field. But if it's an electric dipole, which means that you've got this structure, like the atomic structure, the molecular structure, which is neutral. If you're further away, you're not going to be able to pick up any sort of electric field. But if you come close enough to this structure, you're going to be able to pick up the electric field because of the charge separation. So that's what it means. All right, so the formula for that is important in terms of the multiple choice. All right, so let me show you where the formula is. So the formula of that is going to be important because of multiple choice. Okay, so let's just go, let's take a look at that. All right, so here's the formula for the electric dipole. So the P is going to be your dipole moment that you got. So it's the net charge and the separation of the net charge. All right, so dipole moment is going to be pointing from negative towards the positive charge. And notice that this electric field is going to diminish radially as the cube of the distance. All right, so okay, so electric field due to a line charge, So the electric field due to a line charge. Yeah, you need to practice this for the Tuesday's extra credit test. All right, just practice it. All right, so practice the hydrogen atom, practice this. All right, my derivation is good enough. If you want to watch it and then just go through it step by step until it makes sense to you, by all means do it. So this is due to a line charge. Okay, forget the mathematics of it. So the electric field due to a line charge. There's a formula that we came up with. Let's get back to the formula. Electric field due to a line charge. All right, so that's the formula that we came up with. And okay, that formula is not that interesting. So, and then get the one for a charge disk. All right, so the charge disk is the one which is more interesting that we will get to use. All right, so here is the formula for a, this one is for a charge ring, and this one is for the charge disk. Okay, so these are the formulas available in case there are multiple choice questions. Okay, so don't memorize these formulas. Okay, the only formula that if you have to commit to memory, just commit to memory this one and that one. Okay, I wouldn't memorize these formulas. Okay, so these are the derivation results. So this is a charge disk, and this one is a charge. This is a charge disk. This one is a charge ring, and so that's what the solution should look like in case there are multiple choice questions. All right, so these are all the questions out of that. All right, so there's one more that I need to. Okay, fine. Okay, so also check to see if you can do a problem like this. Okay, so let me point out a few things that should help you. Okay, so this one is better, I think. So these are my lecture notes. So the Bohr's atom problem is here. All worked out. I like my solution better from the lecture. All right, this solution is probably from Haldane and Resnick. Mine is better than that. There's some example problems if you want to look over them. All right, so this is problem number 3. So the problem's done in class. I don't know why this is not showing right now. It's on this computer. The problem's done in class. You should be able to find them here. So here's the electric field due to an electric dipole. And here's how you get to use the formula. All right, so here's the problem, here's the solution. Electric field due to a line charge. All right, I think this derivation is from Haldane and Resnick originally, which is the same as the electric derivation. Electric field due to your charge disk. All right, this is from Haldane and Resnick. Mine is better. All right, so I would definitely use the lecture over this. I don't like the way Haldane and Resnick ended up doing it. Okay, so they extended the charge ring into a charge disk. Transitions got awful, so I'd like my approach better than this one. It's a dipole in an electric field, so we didn't really discuss that. So stuff that we didn't discuss, don't worry about. All right, so okay, so what else do we have here? All right, so that's good. So run over that. All right, so we didn't go over these yet. So unit charges, you got positive and negative unit charges. Experimental proof that there are two kinds of charges is the charge objects will either attract or repel. So you can explain the attraction and repulsion using two kinds of charges, right? So the like charges will repel, the unlike charges will attract. That's it. Net charge is the sum total of all charges within a given region. It could be positive, negative, or it could be neutral. Meaning of conservation of charge, the charges cannot be created or destroyed. Ionization is the separation of charges from atoms. Stripping electrons from atoms. There are 3 ways you could do it: friction, heat, and or light. Meaning of some positive charge is the region has a net positive charge, which means that it's got more positive charges than negative charges. If something is negative charged, it's got more negative charges than positive charges. If something is neutral, it's got equal number of positive and negative charges. The process responsible for the clouds becoming ionized is friction among ice particles, and we don't know what causes further separation of the charges inside clouds. That's an unknown. Conductors are good at conducting charges because the octet field is not satisfied. The insulators are not good at conducting charges because the octet field is satisfied. Polarization is a process of moving opposite charges to a surface of a insulator usually. or it could be a conductor as well. It doesn't matter. Okay, so polarization is something that happens when you bring a charged object near a neutral surface. Opposite charges are pulled to the surface. The like charges are repelled to the surface. So it's something that happens when you bring a charged object near a neutral surface. So the balloon becomes attracted to a neutral wall if it's negatively charged because of polarization. Volume water becomes attracted to a negatively charged rod because of polarization. The water molecules are polar molecules. Earth, which is initially negatively charged, becomes positive charge after the charge separation inside the planets because of polarization. Electrostatic force is the force between charges, and the Coulomb must have known that the force decreases inversely with the distance because of polarization. All right, when paper becomes polarized because of a negatively charged rod, the opposite charges in paper are closer to the negatively charged rod than the like charges. All right, so the force of attraction is going to be more dominant than the force of repulsion as a result. Electrostatic force is similar to Newton's law of gravity because both of them are inverse square laws. They got the same mathematical format, and they differ in a couple of ways. Gravity is attractive. Electrostatic force can be repulsive. Gravity is weak. The electrostatic force is extremely strong. So the electric field is an electrostatic force field. The idea came about because one needed to explain how the force could get transmitted without any physical contact between the charges. So how does the force get transmitted through space without any physical contact between the charges? So the only way you can explain that if you have some kind of an electrostatic force field. So that's how the concept came about. So describe the relationship of positive and negative charges to the electric fields. Positive charges are the emitters, transmitters. Negative charges are the receivers. What happens to a positive charge interacting with the electric field is that the electric field is going to induce a force on the positive charge in the direction of the electric field. And then the charge is going to accelerate in the direction of the electric field. What happens to the negative charge interacting with the electric field is that the negative charge, the negative electric field is going to induce a force on the negative charge in the opposite direction of the electric field. And the negative charge is going to accelerate in the opposite direction of the electric field. So what happens to a neutral object interacting with the electric field? It's going to become polarized. And depending upon the geometry, if it's near the source of the field, it's going to start to move. It's going to experience a force in the direction. It's going to experience a force towards the source of the electric field, and it's going to accelerate towards the source of the electric field. So the best place to be during an electrical storm is inside a metallic conductor or enclosure, more like it, nothing. Okay, so the best place to be is inside a metallic enclosure, like a car, airplane, anything made up of metal, anything made up of a conductor. The reason is because during an electrical storm, if there's lightning or any sort of spark, spark is going to transfer charges, a net charge, to the metal. It's going to deposit net charge to the metal, positive or negative, and the like charge. So the metal is going to acquire a net charge as a result. It's positive net charge or negative net charge, meaning that it's going to have excess positive or negative charges. So excess charges will repel each other to the surface immediately. The furthest that they could be repelled is going to be the surface. So the like charges will repel each other. So, and they're going to try to get away from each other as far away as possible. And the furthest that they can get away is going to be the surface. So which means that if you're inside of that metallic enclosure, you're going to be 100% safe because those charges won't be able to penetrate into that metallic enclosure. All right, those metallic enclosures are known as the Faraday cages. And again, Faraday is the guy who's responsible for giving us all the physics that we're going to be discussing this semester. The guy who couldn't do math, but he was able to visualize this in his head. Just imagine that. All right, so that's as far